Welcome. This is a fictional visualization of what day-to-day collider physics might involve in the year 2030. I want to propose one possible future, and if you disagree with some of it, then you should create your own version of the future, and we can discuss them concretely. In this future, we'll follow Maya as she logs onto Collider Lab, which is a platform for collider physics in the near future. So the year is 2031. Maya is a PhD student. She's affiliated with the High Lumi MC meta collaboration. Meta collaborations are cross-detector communities that police their own standards, monitor their own publications and resources. The meta collaboration structure was introduced after the Swiss government ordered an immediate opening of all data that enters a software system. So this means that high-level trigger is now legally required to store all events at full granularity, around 1 megahertz across Atlas and CMS. So the meta collaboration system stepped up to fill this gap using space across Android phones. Around 50 exabytes is currently available in general across the Android ecosystem on consumer devices. In fact, we can see a heat map of some of these devices from meta collaboration members in the High Lumi meta collaboration. Each event is stored on at least 2 devices and hashed to ensure that it's recoverable, and we thank Google for supplying this access efficiently. Maya herself stores some of the data from her meta collaboration on her hard drive, a few terabytes, as you can see here, and that's more than average. It earns her some credit. She leaves her machine on at night as well, so the MC can run simulations. What does she spend her credit on? Well, what does any student need credit for? GPU hours. So let's spend some. Maya is working on a little idea in a bubble of foundation space. Right, what is foundation space? Foundation space is a latent representation, and all events that are stored in real time are embedded into foundation space, which is around 100,000 dimension latent space. And most of this is mapped topologically to the standard model. And you can see that as events come in throughout the day, from Atlas and CMS in this case, we have events arriving into foundation space, and you can see that most of them are comfortably within the surface of the standard model. In particular, certain popular processes are mapped into this representation. How can you interpolate a surface into 100,000 dimensions? You would need differentiable simulation. Well, matrix element calculation and parton showering has been differentiable and GPU based ever since MagGraph 6 and Pythia 9 came out. And you can read more about those software in the documentation. But material interactions, detector digitization, aren't these stochastic and non-differentiable? And the answer is yes, they are. In Giant 5, this is still the gold standard. But we can turn Giant 5 into differentiable mode, and those few non-differentiable steps are replaced with generated models, which are nice and differentiable. So building the standard model surface is then tractable. We only need to do it once, and then it's tuned over time. But it means that we can confidently report when events are recorded as possible anomalies outside of the standard model manifold. You can see that as more HL-LHC data is gathered, more little anomalous bubbles appear outside the standard model surface. Some of these are squashed by operations teams of AI agents, which are reinforcement-trained detector alignment calibration agents, for example, in tandem with humans, of course. Some are just some very long tail events that need some NNLO modeling. And the modeling agents collect these and work with human theorists, lattice phenomenologists to update the models. And you can see, for example, detector calibrations are specific to each detector. Here we have in blue CMS and in red Atlas, and of course where bubbles are anomalous for only one of those detectors, that's probably some detector miscalibration. But some bubbles of anomalies are just weird. And we can see one here at around 4 p.m. today. There was a strange anomaly appearing in both Atlas and CMS just outside the standard model surface. You can see that it appears over the course of around 10 minutes at both detectors, which is a little odd. Maya, who is a climate scientist, is working on this bounty, and she has this idea. So, as I said, you can see over the course of a few minutes this anomaly appear and disappear, and it appears for both Atlas and CMS. And of course, this is only really possible with hit-level open data from all the collaborations being available in real time, minutes after they're collected. And that's been the standard ever since the HL-LHC first started taking data. It was a headache at first, of course, but now it's invaluable. So let's have a look at a few events. We're actually going to take this bounty with Maya. This is an active bounty, which is worth around 15,000 credits. You can see a couple of examples of these events in the anomalous bubble appear in the Atlas detector and the CMS detector. As I said, this is only possible because we have real-time open data down to hit level. They look pretty normal, a couple of jets in each one. But if we turn on the reconstruction error from the foundation space, we can see that some of these hit regions have high anomaly scores in both the Atlas and CMS events. Two events, two detectors in the same instant, an anomalous shower in each detector. Maybe it's a cosmic ray, but why is there an increase over time of the order of minutes in foundation space? Maya has a theory, but to test it, she's going to need to run a simulation to train a fine-tuning of the foundation model in order to calibrate it to real data. She wants to simulate the sun. Now, sun models don't currently exist in Collider Lab, so she needs some domain expertise from her climate science training to pull the right libraries in. So she's going to search for a few libraries and ask the Collider Lab AI agent to piece together the relevant modules. So she's going to use the Solaris solar flare sun simulation. And okay, that pulls a sun model and a solar flare model, and of course pieces this into the LHC collision matrix element generation, and then detector simulation and digitization. And it sets up the workflow for us. And we can play with some of the parameters of the sun model and solar flare model. And the AI agent helps glue these models together. Maya has never heard of Gaudi or CMSSW or Athena, and she never will. She never needs to. Of course, if this were a vanilla Collider model running an analysis, and that's a whole other story, how analyses are run in 2031, which we can talk about in a different video. Of course, if this was a vanilla analysis with Collider models, then the fast simulation is free and almost perfect. It's down to within quantum uncertainty. But sun simulation is new, so she needs to spend some credits actually running Giant 5 to get a full simulation. She'll probably need a few 100 million events. So she waits a few minutes for this to come through. How is this so fast? How can we simulate hundreds of millions of full simulation Giant 5 events in a few minutes? Well, one thing is that the systems are just ready to go. So ever since Sirius, which is the simulation, reconstruction, and analysis as a service, ever since Sirius became the standard across all collaborations, the major channels and configurations are precompiled and just sitting there waiting on API calls, trivially able scale across hundreds of thousands of nodes. And since everything was ported to GPU, what used to be heterogeneous is actually now homogeneous. Everything is on GPU and lightning fast. That's around a 2 order of magnitude speed up for Geant 5 over Geant 4, even on full simulation. And this is, she just waits a few minutes for the simulation to come in. Once the simulation is finished, she's going to need to calibrate the foundation space model to match how her simulation actually looks in real data. Even the simulations of Geant 5 are not going to be perfect. So we can look at what her simulation looks like. There it is in yellow. She's simulated both Atlas and CMS. And of course, it doesn't quite match the anomaly that we expected. So we're going to need to calibrate it, which uses adversarial unfolding, a technique created by Sarah Chen's group in 2027, which allows unfolding all the way from pit level back to foundation space. It's pretty expensive, and this is what the bulk of her GPU credits are going to be spent on. So we'll calibrate that now. Luckily with LoRa, with low-rank approximation fine-tuning, these kind of fine-tunes are not prohibitive to the foundation space model. And you can see that as the loss decreases, we've unfolded correctly, and indeed her simulation perfectly matches the anomalous bubble. One sanity check, let's plot it through time to see if her simulation matches the sort of time scale. Yeah, and it does, almost perfectly. So her hypothesis was spot on. So of course, now she's excited. She's going to message her meta-collaboration PI, Shirley at KTH, who responds that this is really, really cool, and she should present at the next MC Anomaly plenary. And because she's made a fine-tune to the foundation space model, she should make a merge request. So she's going to git commit her Solaris simulation and calibration to the foundation space model. And of course, some agents and humans will review that commit, and if it matches all existing standard candles, then it'll be pushed through so that the next person doesn't need to make the simulation. Now, I know what you're thinking. Who's paying for any of this? Well, in 2026, Victor Novak, one of the leading machine learning advocates in CERN, went drinking with James Park, who's the CEO of Apex AI. He got him incredibly drunk and hooked him on the idea of confirming or disproving the stability of the Higgs vacuum. Now, we all know this is a long shot, but he committed all free, meaning unused, GPU hours from their new data center to any work that progresses this question. And in 2029, they built a 10 gigawatt center, which is around 10x the combined capacity of all EU gigafactories. And 10% of this 10 gigawatt center at any time is idling. This equates to around 1 million GPUs for HL-LHC research, which is not attached to any institutional collaboration. It's instead attached to the meta-collaborations. The Higgs stability measurement then is ostensibly the thing powering the whole Collider Lab system. It is the engine that gives resources to the foundation space model. So we need to be able to track the Higgs stability measurement, since it is the key metric. And indeed, it is updated in real time. We can see here, you can see the Higgs events being gathered in real time, and importantly, di-Higgs and top events. The combinations of these in the standard model terms are what give us, with the running with energy, the stability or instability of the Higgs vacuum. It's almost certainly going to land on metastability, and we'll probably know for sure by around 2035. And you can bet that. I mean, you can literally bet on the stability or metastability of the Higgs vacuum. And of course, the odds are really leading towards metastability. You can bet on any of the analyses happening at the HL-LHC, and indeed that is a major way that GPU credits are generated and distributed. Let's find an interesting one here. We have Higgs trilinear coupling. It's starting to look like this will be in excess of the standard model prediction. So what started at around 50% uncertainty, then 25%, is now closing in on a few percent already with only 1 year of data. How is this possible? Well, of course, storage of all level 1 software trigger outputs combined with almost perfect high pile-up event reconstruction on exotic objects, low-level object neural simulation-based inference, recovery of all hidden Higgs channels, event-level synchronization between detectors. And this last one is an interesting one. So at this point, because detector data is made open at hit level in real time, tiny clues of collisions from interaction points at other detectors are possible across detectors. And this last one is Maya's pet project. She's looking for tiny signals of Atlas collisions in LHCb sensors. Ever since SHIP proved that there are anomalous signals that might point to heavy neutral leptons, there's been interest in long-lived particle detection far from the detector. This occurred in, let's see if I can find it. I forget which year SHIP reports an analysis of a detection possibility of long-lived particles. But it has become a very popular topic to investigate in the late 2020s. So some people in the meta-collaboration of Hayalumi came up with an effective field theory that correctly predicts some of the readings at LHCb that could be actually produced in the Atlas collisions. To test it, though, they actually need to put some measurement devices opposite LHCb to pick up these back-to-back decays. So what is that, such a device? That's something that Maya is working on. She's designing some detectors that could be 3D printed. At this point, detector design is completely trivial. It's drag and drop and modular, and we can try out lots of different detector designs in real time. And because at this point they are fully differentiable, we can look for certain detector designs efficiently that are particularly sensitive for these long-lived particles. Still, choosing materials, components, and so on is non-differentiable. It's still combinatorial, and so human intuition is useful even for detector design. And of course, it's aided by AI agents. One agent suggested some small set of CCDs scattered around randomly, sort of like this, but even more random. And after some running these simulations, it turns out to be a very cheap way of detecting these long-lived particles near the Atlas detector. And of course, these could all be 3D printed, and the sensitive material could be pulled from commercial smartphone cameras. But then it occurs to Maya, hang on, we could look at the collection of meta-collaboration members. And there are a lot of meta-collaboration members living around CERN, of course. So we can actually zoom even into, say, the Atlas detector and see how many smartphone owners from the meta-collaboration are right near the Atlas detector. There are some hundreds. Now, we could be interested in asking how many of those live in the back-to-back region. So we could say, give all MC members in a 30-degree beam north of Atlas. Nope, that didn't work. Let's try one more time. We want to filter only to members in a 30-degree beam north of Atlas. And so, as we can see, there is a sizable collection of members in the back-to-back region. Now, all of these members already let the meta collaboration run simulation and training overnight on their computers and their phones. Couldn't Maya simply ask them to face their cameras towards Atlas while they sleep, and she could use their silicon, say, for a few weeks of data taking? And maybe her PI, Shirley, could even sponsor the project and offer GPU credits to participants. She makes a note to bring this up at the next meeting, but for now, she logs out. Now, of course, this is speculative. It's unlikely that this will all happen. And indeed, I would say there is a less than 5% chance of all of these events to line up. It requires a lot of technologies to converge simultaneously across not only machine learning, but also infrastructure, and politically for organizations to agree, especially around open data. But I think it's interesting to plant the flag in a particular version of the future and discuss which technologies, which political choices are good, which ones are bad, which ones are possible, which ones are impossible. And then once we have an idea about what that future scenario could look like, we can actually start talking about how do we get there. If you agree or disagree, please visit Collider2031.com or go to the GitHub and send a message, post an issue if something doesn't work. If you want to try and use this platform to build your own version, reach out or simply fork it and ask Claude to do the hard work for you. Thanks for watching.